question here is going to be vector projections. And this is the big this is one of the biggest topics in the vector unit. We'll be using this a lot in grade in this unit and the next unit. Okay, so vector projection is pretty big. So we're going to say here, think of the projection of V onto U. As the shadow that V casts onto U. It is a vector with the magnitude of the, I don't want to say X, I'm going to say that. With the magnitude, yeah. Shoot. The magnitude of the, in the direction of U. I'll draw a picture. It's hard to, it's hard to say. Okay, so this is my picture, okay? So this is V, this is theta, this is U, is that giant vector right there. This vector right here, and this is going to be actually a vector this time. This is called vector projection. Right there. Okay. Now you might say, why is that weird? The difference is it's actually a vector. Instead of multiplying things, we're actually creating a vector out of it. So think of it like a shadow. Okay, sorry, Matt, I'm going to use you as an example, okay, or your desk. How about if I'm putting my arm up like this, my arm is going to be the vector. The second vector is going to be the table. Basically, the projection of my arm onto the table is like the shadow of my arm on the table. So think of like the x coordinate of my arm. If you think of back in the Spider-Man questions from grade 11, it's like you're looking at my arm from heaven. What do you see? You only see like the x coordinate this way. The difference is in vectors, it doesn't have to be just x. The two vectors can be all over the place, right? That's the difference, okay? But if you think of it in 2 dimensions, right, you're thinking it as, again, if you're looking down from the ceiling, you're only going to see the x coordinate of my arm. Is that the idea for that? That's the idea of the projection. Okay, so it's a new vector with the same direction of V, with the distance of the x coordinate of V. Does that make sense? Not really. Let's stick with it, okay, and see what happens, all right? So the equation for this is, if I can get it. Oh, I should also say, if the angle between V and U well, we'll leave it that for a second. Just can I finish my note, Michael, please? Oh my goodness. If the angle between U and V, that'll be next one, is between 90 and 180. Then the direction of is the opposite of U. And I should say here, I'll get out of the way here, sorry. What this is translated out is the projection of V onto U. Okay, that's what it's written as. Now, Michael makes an excellent point. Michael, can you share with the class what you whispered to me there?
Well, if the angle between V and U is 0, so if they're collinear, then it'll be V.
Yes, that's going to, the projection is going to be V. Also, if the angle between them is 90 degrees, what's the projection going to be? The 0 vector. There'll be no projection, right? Okay. All right. So I should say for this
And
here,
it's good to remember that it's V onto U. You're,
yes,
like, when you read it, you're like, oh, project U onto V, but no.
we're going to say then if V is perpendicular to U, then V casts no shadow. So if theta equals 0 degrees, the projection of V onto U is equal to 0. Okay, the equation for it.
It'd be V.
No,
If theta equals
oh,
0.
sorry, 9 degrees, sorry about that. Thank you. Thank you. I think you're here, everyone's notes would have been totally mixed up here. Okay, so instead of texting all our best friends, what we should be doing is focusing right now, okay? Okay, so there can be no projection. All right, so let's go through the actual equation for this, and then we'll get to all this, and then we'll get to work, and then we'll be done. Okay, so the equation for this is the projection, and this is one to memorize. The projection of V onto U is V dot U.
Where we apply dot product right here.
Divided by U dot U times vector U.
So it really matters which one you're projecting onto which one here.
Yes, it totally does. That is something you will have to commit to memory. Now, the thing is that you can help to remember yourself for this is, whatever the small letter is, there's 3 of them in your equation. Okay, there's that. Or 4 of them, I guess. The V is only a little bit, everything else goes from that. Okay, once you do a few of these are really easy, but the idea is you have to get the equation down. And I'm going to say again, we'll be using this again when we get to the 3rd dimension. So this is something fundamentally important for this course, okay? So what this is doing is this is combining vectors. Okay, that's what this is doing, okay? So it's getting, one of the applications of this, again, I use this in computer science, okay? For anyone doing, anyone here play video games? No one does, you're teenagers, okay? So no one, of course, plays video games, okay? But if you're playing a video game, right, and the idea is you're only viewing what you're looking at the closest objects to you at a time, okay, right? So they're actually deciding what is being drawn in the background. So what a vector projection would be, again, if you're showing a picture of, let's say, a bar going from me to Evan, okay, right? And if you're looking from Ben's point of view, you're only seeing the projection of this bar onto the horizontal plane in front of you, if that makes any sense, okay, right? So you're not seeing the entire bar, right? Again, you're just seeing part of it. And that's the same thing. All sorts of movies do this sort of thing too. So if you ever watch Shrek, which some people have, okay, right? Any sort of cartoony things do all this sort of thing that we'll get into definitely for this. Maybe not with the heavy duty mathematics, but the computers do this sort of thing all the time. Yes?
Okay, I don't understand how the projection of V onto U is like opposite U.
Oh, the direction is opposite, okay? So think, if the direction goes from 90, sorry, excuse me for a second. If the direction goes from 90 to 180, let's pretend it's out here. The projection for V onto U is going to be this way then.
But is it still going to be like on that same slope?
One second, so let's say I do U is like this, and there's V, okay, and there's your theta, and there's V, okay? So what's going to happen is here, this dotted line is going to go like this, okay, but what's going to happen is the projection of V onto U is going to be in that way. Okay, that's what I meant by that. Okay, so it's possible to go in the opposite direction. Okay, pouring you that much to the washroom, okay? I'm sorry to hear that.
Wouldn't the angle be from like 90 to 270?
I guess technically, yeah. We're going to stick with 0 to 180, I think.
Then if it's down here, I think.
Yeah.
I thought you said that if, like, if there was a bar from you to Evan, and from his point of view, he only sees this part of it,
Yes.
then why is that angle rather than straight? Like, if I was to draw, this is you, this is Evan,
Yeah.
and Ben is here, and he only sees this. Would this be the projection?
The projection, but the thing is, I was going that way. I was going like Ben is like this. Okay, so if you get the projection from here to here, that would be the projection from here to here. That's what we're saying. So his projection would be like this. So you only see based on that. Let's go with some math here for a sec. Sorry, who's the bigger soul? Start with that player here. Let's do a little bit of math here. Example 3, we're on to? 2. Example 3. On to 3. Okay, we're going to say, find the projection of U onto V if magnitude of U is equal to 8, magnitude of V is equal to 12, and theta equals 39. Let's try again. You want to do this one? Yeah.
You use the cos theta. You right?
Yeah, we can do this one. Okay. Okay, so let's go through this if we can here, okay? So I have my magnitude U, magnitude V, and I have my theta. Can somebody give me the equation for the projection of V onto U? Of U onto V, sorry, V onto V. Close, but opposite, I tricked you. Sorry. So this is going to be, yes, the exact opposite of what you say. Now this is the thing, guys, okay? We have to be aware when you're doing this, okay? So the projection of U onto V, U is the big one, V is the little one, right? So this is then going to be U dot V over V dot V, and then by V. Okay, are we okay with the first step there? This is just subbing in equations. Okay, now this is the trick, and I'm a tricky human being. Jeff, what's my equation for U dot V going to be in this case? Which version are we going to use of U dot V?
The cosine.
Sorry, go ahead, help me with that.
The cosine.
Why does the cosine one have to be in here?
Because you have the magnitudes and then.
Yeah, I have magnitudes and I have angles. I don't have any points, right? If I had Cartesian vectors, I'd use that version. So I'm going to call this then. What you guys were saying, please?
The magnitude of the projection.
I guess probably it would turn into that, wouldn't it?
Yeah.
We'll deal with that.
Because we're not given the Cartesian vector.
With this, I guess, yeah, I'll do that. Okay, are we okay on the logic of what's happening there so far? So far, so good? What is cos of 0 equal again? Oh, goodness. One person passes trig. That's good. Thank you, Nate. 1. Magnitude of U should be 8 times 12 times cos 39 all over magnitude of over 12 times 12.
Why do you know it's cos 0 again?
Because cos is the x component, so with that it's 0 here.
Well, okay, just think, okay, let's go user, I'll help you out user, and that's true. What you're saying is true, I'm going to help you. If I have two vectors and they're the same, what's the angle between them? Okay, right, so V and V, they're the same direction, so it's going to be now. So what this turns into, I keep going here, 8 times 12 times cos 39, I think I got as, I can't do that in my head. What is it? 74.6, you said? Times 144 times vector V. I'm just going to leave it as vector V for right now. So therefore the projection of V onto U is equal to some fraction of the vector V. What's that fraction, please? I don't get a decimal for that. 0.5 something? 0.51?
You could do 5 too.
0.5. Okay, so basically it's going to turn into 52% of whatever vector V was. It's going to give the same direction as V. Okay, this works a little better when you deal with Cartesian, which is going to be the rest of the examples here today. Now, one for that trick, I'm sorry for tricking you. Okay. Okay, but the idea is you're saying you want to be means that these will work. Okay, so just have to remember that. Okay, here comes example 4, and I want you guys to try this one for me right now. Are you ready to shine? Why do you guys put yourselves down? You can do this. You guys are all highly intelligent human beings. Nate, you're very bright.
Everybody laugh.
Why is everyone laughing?
You'll show them. Just run in the room. I'll show you all.
Okay, here comes the question we will see on your tests. It says, find the projection of A onto B. If vector A is equal to 3, negative 5, and vector B equals negative 1, 8. All right, now before I let you guys to do this one, since these are Cartesian vectors, what version of the dot product are we going to use? The simpler one, right? So that if you're going to add the coordinates, we do not need any angles in here for this one, okay? Now, when you do this equation, this is all going to turn into a scalar, and this is just going to stay as a vector. So you'll be multiplying a vector by a scalar in your final answer, okay? So if you're confused about that, don't worry about it. Do as best you can. We'll get there at the end. Okay, so do this. We'll give you some sort of decimal or fraction. It will give us fractions in this course, of course. And then they're going to times that by the vector at the end. Okay, I'm going to pause in the video. I want your self-confidence in yourselves. You guys can do this. It's new and scary. The problem with these ones, I've realized this is a lot